Right, let's look at the next form of 0 times infinity. And so the original process for evaluating limits using L'Hopital's rule works if your original limit is in the form of 0 over 0 or infinity over infinity. Now the other indeterminate forms need to be manipulated to get them into the form of infinity over infinity or 0 over 0. And so when we start with 0 times infinity, right, the limit as x approaches 0 from the right of x times the natural log of x. X is approaching 0. Right? Again, think of your natural log of x function as you approach 0 from the right, your function values are going to negative infinity. Okay. And so again, this format works for 0 times positive infinity or 0 times negative infinity. So our job here is to rewrite this, because I know that if I have a limit that's equal to 1 over 0, that limit would approach infinity. Right? If you have the numerator is a fixed value, the limit, and the denominator goes to 0, then the whole fraction will grow without bound. And if you have a limit that ends up in the form of 1 over infinity, we know that is equal to 0. So I can do one of two things. I can rewrite x in the denominator as its reciprocal, or I can rewrite the natural log of x in the denominator as its reciprocal. So we're going to rewrite this as the limit, and it's a little confusing until you see it. I'm going to write this as the natural log of x divided by 1 over x. So if I have an x in the numerator, I can the product of x and the natural log of x is the same thing as the natural log of x divided by 1 over x. So convince yourself off to the side here by just doing the algebra. When you divide by a fraction, you multiply by the reciprocal, and you get x times the natural log of x. Your other option would be to leave the x where it is, and then rewrite that as 1 over the natural log of x. If we do that, we end, if you double check that, x divided by 1 over the natural log of x, that's the same as multiplying by the reciprocal, so that would be x times the natural log of x over 1, or just x times the natural log of x. But you have to remember that in your next step, you have to take the derivative of the numerator and the derivative of the denominator. So you're going to ask yourself, which is easier to take the derivative of, 1 over x or 1 over the natural log of x? And the answer is 1 over x. With the 1 over the natural log of x, you would either use the quotient rule, or you'd rewrite this and have to use the chain rule. This is much easier to do. So we continue using L'Hopital's rule. We take the limit of the natural log, of the derivative of the natural log, which is 1 over x, divided by the derivative of 1 over x, which is negative 1 over x squared. Here is where you do a little algebra, because if we try to evaluate this limit right now, we end up with infinity over infinity again, and we're still indeterminate, and we could keep taking derivatives and we'll still get indeterminate forms. So at some point you always want to double check and see if you can use some algebra to simplify. So this expression right here, we'll do this off to the side. If we have 1 over x, that's going to be 1 over x times negative x squared over 1. And the x's are going to cancel, and we get negative x. So this is equal to the limit as x approaches 0 from the right of negative x, and the limit of this is equal to 0. So just to summarize, when you have the limit in the form of 0 times infinity, you want to take one of the functions and rewrite it as its own reciprocal in the denominator. And then what you've done is you've forced 0 times infinity into either infinity over infinity or 0 over 0. In this case, we forced ourselves into an infinity over an infinity, which is why we were allowed to use L'Hopital's rule again. Okay, another form that can be rewritten so that the indeterminate form will be 0 over 0 or infinity over infinity is infinity minus infinity. And the trick here is to combine the two fractions as one. When we evaluate the limits separately, we 1 over, as x approaches 0, of 1 over x, and we're approaching 0 from the right, so put a little plus sign in here. If we're approaching 0 from the right, we're going to get infinity minus infinity. And again, since all infinities are not created equal, that infinity minus infinity is not equal to 0 necessarily. It may or may not be, again, depending on how fast one grows as opposed to the other. So we're going to use some algebra to rewrite these two functions as one fraction. If we have 1 over x, leaving a little space, 1 over sine x, I'd want to multiply by x over x, by sine x over sine x. So my new limit will be sine x minus x over x times sine x. So I end up with 0 minus 0, which is 0, over 0 times 0. So I now have basically forced this form into 0 over 0, and I can use L'Hopital's rule. So at this point, all I've done is manipulate algebra. I haven't used L'Hopital's rule yet. Now we'll use L'Hopital's rule by taking the derivative of the numerator and the denominator separately, taking the limit as x approaches 0. The derivative of sine x is cosine x. The derivative of x is 1. In the denominator, we have to use a product rule. So x times cosine x plus sine x times 1. At this point, we substitute the cosine of 0 is 1, so 1 minus 1, I get 0 in the numerator. 0 times the cosine of x is, or the cosine of 0 is 0, plus the sine of 0 is 0. So I end up with, I've got 1 minus 1, which is 0 in the numerator, and 0 plus 0, which is 0 in the denominator. I have to use L'Hopital's rule yet another time. Since they're already in sines and cosines, there's not a whole lot I can do here to simplify this fraction, so we'll do one more iteration of L'Hopital's rule and hope we get to a form that's not indeterminate. The derivative of the numerator is negative sine x. The derivative of the denominator, I have to use the product rule on the first part. So first times derivative of the second, so x times negative sine x, plus second times derivative of the first, so cosine x times 1, then plus the derivative of sine x, which is cosine x. And at this point, I mean, you can simplify the algebra a little bit, but really it's not necessary. If I just substitute in the sine of 0 is 0, 0 times the sine of 0 is 0, the cosine of 0 is 1, cosine of 0 is 1, and we get 0 over 2, which is 0. So we do have a case where the original limit was in the form of infinity minus infinity, and the answer did come out to be 0, but it's not guaranteed to be that way. Sometimes infinity minus infinity is equal to 0, and sometimes it's not. So you need to do the analytical work to show your final answer.